The scientific revolution starts now.
The Demystified Podcast.
Let us see in the dark.
At present, I'm the science director for the Foundation for the Study of Cycles, and I also run Cycles Research Institute. But now that we've joined together with them, that's sort of just the historic things mainly. I guess I first got interested in cycles as a teenager when some family friends gave me the Sky and Telescope magazine for my birthday, and they did that for a number of years. So I had lots of these, and every month it had the sunspot numbers daily. So I thought, wonder what these are good for, because I knew there was an 11-year sunspot cycle, but I started graphing them, and there was a 4-month cycle. I thought, I've never heard that one mentioned before. So I started looking what happened in 4 months. And after a while, I realized that Jupiter, Venus, and the Sun made a straight line every 4 months. And Jupiter and Venus are the two planets that have the strongest tidal influence on the Sun. And it so happened that the peaks in the sunspot happened exactly when they were in a straight line. So I started looking at other pairs of planets that had reasonable tidal influence, and sure enough, each of them had the same thing. At that stage, my mode of transport was a bicycle. I rode my bike into town, went to the main library, and I started looking up books on the Sun, and I found they had none of the modern books mentioned except one, and it said in the 1800s somebody suggested exactly what I described, and they said, personally, we think this will just be disproved with time. And I said, haha, you're wrong about that. It's been proved with time. Later on, I discovered there were a few other ideas on how the planets influence the Sun and the sunspots. But during that was in the 1960s. I was doing that, and in the 1960s.
And what was that? What did it feel like? Did you feel like let down by the fact that other people weren't working on the story? Did you feel excited because you thought you'd be able to share it with people?
No, I did have that on some other occasions, but they worked out very well. Later on, when I found the Foundation for the Study of Cycles, I used to have people that said, these cycles you found, they're just random things. It's not real. It's not anything. And there were proper statistical tests, so I knew they weren't. But when I came across Edward Dewey's work, and I found he'd found much of the same stuff as me, and he was using different data from different time periods, different countries, and he'd found very accurately the same period cycles in them. So at that stage, if anyone ever tried to make any doubt in my mind, they had no chance whatsoever.
Now, who is Edward Dewey?
So Edward Dewey was the man who started the Foundation for the Study of Cycles. I found out about him in the 80s, by which time I've missed a bit of the story here, because so that was the 60s when I was doing Sky and Telescope magazine sunspots. Then in the 70s, or in the 60s, I also started working later on in the 60s, and I did work for an investments department in the company I was in. So I got interested in that because I thought you can make some money if you can predict the share market. I started looking at the share market and didn't have enough money at that stage, but later I did. And then in the 70s, I started looking at this seriously, trying to do forecasts for businesses of business conditions. They want to know interest rates, exchange rates, all the usual stuff. And so that was okay. I got a lot of data, and I started analysing it. And so our cycles jumped out at me. I wasn't looking for them, but there they were. I decided I got to try and work out how long these cycles are. Now, I've done a little bit of that stuff in university, but it doesn't really sink in because the people that are teaching you don't really know what it's for or how to use it. So you've got to find someone that does that. But so I started doing cycles analysis, and it worked. I got some things that worked okay, and I found there were 4 cycles I could find in the New Zealand economy where I live, and the periods I got were 4.45 years, 5.9 years, 7.15 years, and 9 years were just a little under. Later on, when I came across Edward Dewey at the Cycles Foundation, that was in the late 80s, I went to visit the Cycles Foundation. I went a week before their conference, and I gave a talk there. And when I arrived, and sat in the library for a week studying all the past stuff that had been written. The guy who was the chief executive at that stage sort of wandered through each lunchtime going to and from lunch, and he saw me there each day, and so he came and introduced himself and said, "What are you doing here?" And I said, "I'm reading all your stuff. I've come from New Zealand." And so he said, "Would you like to be one of our international board members?" I said, "Sure, but you don't know enough about me." He says, "I know enough." He said, "The last guy that sat here for a week ended up as the chief executive." He was talking about himself. So he knew if I had that much interest, something was bound to be there.
And those cycles that you were talking about, those were in financial growth of some sort?
Yeah, well, so the ones I was doing, it was aimed at economic ones, but I also included some demographics because I thought that was also important in trade and stuff, you know. So it was 22 different variables I put in. So when I came to do his paper, there's one called The Case for Cycles, and I highly recommend anyone who's got an interest in this to read that paper. You can find it on cyclesresearchinstitute.org. Look for The Case for Cycles by Edward R. Dewey. And in that, he lists loads and loads of cycles he found in different things. And he has a little summary table, which is an interesting one. It's got... now, Pythagoras had understood the frequencies of music, and he has this table that's shaped like that, a lambda. And it starts off and he goes by ratios of 2 one way and 3 the other way to get the notes, because in his opinion, all the notes were made by ratios of 2 and 3. And in fact, you get most of them that way, but not all of them. Later on, the father of Galileo corrected him and said there's a ratio of 5 in there as well, and there is. And some other people, like in blues music, they have a ratio of 7 as well. So those need to be there, but most of these are done in Indian music. They have a 7. But he had...
Although, to be fair, you can actually just keep going in terms... If you just move up in fifths, you'll eventually get back to the... which is 3 to 2, yeah. That's
what Pythagoras tried to do, but it doesn't quite come back right. You miss.
That's true. It's not tempered.
It's called Pythagoras' comma. Galileo's father sort of solved that, because you don't need to do that. In Indian music, they do move around all those things. We can explain that later, I think, if we want to. But the cycles that he had, starting from 17.75 years, he doubled it. Got 35.5, very close to my 35.6. He divided by 2, got 8.88. Divided by 2, got 4.44, very close to my 4.45. Then he divided it by 3, got 5.92, very close to my 5.9. Now, he didn't have, that table doesn't show the 7.15 year one that I got, but he did have that as a common cycle. It's about 7.12, I think he had. So those... So
hold on. I want to before we move on from this. You said that you started from 17. Is there a significant
17.75? Yes,
17.75. Yeah. Where
there's no reason for that one. That just fits.
Okay, all right.
So I asked myself a lot. What's so special about 35.6 years or 17.75 years? In fact, they're just members of this whole series going all the way down. But it's so. Later on, we come to why is it that number? It depends on the whole universe. So, Dewey had...
Doesn't everything, though?
Yeah, that's right. The whole influence of the universe is on everything else. Dewey had collected data and analysed, and when I say analysed, they did it by hand, right? He was doing this in the 40s and 50s and the 60s, and they did it by hand. Eventually, he got computers near the end of his life, but they had ladies that did moving averages, adding all numbers up and subtracting and dividing them and doing this sort of stuff, and they found cycles like that. They did a very thorough job. They collected data on, he says hundreds, but I think it was probably near 1,000 things he had data on, that they had time series. And he said they found thousands of cycles. So in most things, they found more than one cycle. So when you had this table, it was representing the most common cycles, some of the ones that occurred in many different things.
So before we move on from Dewey, I want to point out that there was a lot of criticism of his ideas, right? Like people were very from established economists. People came through and they were like, I don't necessarily think that this is predictive. And so, in terms of how Dewey himself saw his predictions versus how the rest of the world saw them, how do you account for that tension?
It's also worth mentioning that most economic theories are suffering terribly in terms of predictive power.
Like we definitely should. Like economics is what is it? The dismal
trying to predict
science?
share markets is quite difficult because there's a lot of people doing it, and some of them are very clever and got very powerful computers, and they get the data very quickly. But some other stuff you can predict quite well. I gave a talk about this in the 1970s at the statistical conference. And I put up my graphs of the different cycles I'd found, and an economist hopped up and he said, oh, that one's the Kondratiev cycle, this is the Schumpeter cycle, this is the Jevons cycle, and this is the such and such cycle. None of those exist. The only one that exists is the business cycle you've got there, that one. And I thought, that's funny. Why do they give names to things that don't exist? And why am I finding things that don't exist that other people previously found that don't exist? I managed to answer that question for myself at one point. Oh, I should mention, after he did that, a bunch of other people got up and they said, we're in social services, we're in this, we're in that. That's exactly the cycle that we see in our social services or whatever. So they do exist, and they're very real. My view is that economists say they don't exist because most of them are employed by government or government agencies, and they've got to say, this is how you influence things, because they want to believe that governments can change things. And mostly they don't. Mostly the things happen regardless. So they've got to deny...
So it's like they don't want to appreciate the boom-bust nature of economics?
Yeah.
Well, we've talked about this before on the show, where it's the goal of the state is to exert power. And part of power
is... the guiding lights.
And it's the guiding light, and it's the ability to take some action that will change something so you can take credit for the good stuff, and you can say, well, we averted the bad stuff. And so if somebody comes along and is like, hey, it's just noise in terms of what the universe is doing, and and what you're doing is completely washed out by nature. Yeah, I can see why that's an unpopular
Same thing.
story.
I mean, Ray, we just had a gentleman on the show who was noting cycles in the galactic, the orbit of the solar system through the galaxy as it related to climate change. And he's a very well-known physicist, but he's been really given the runaround for even suggesting that, something other than human beings could be in control.
I think that's our God complex at play.
Yeah, anyone who studies long-term cycles will very quickly come to the conclusion these things have been going on for hundreds of millions of years and are very clear and huge cycles that have massive effects. You can do a whole talk on that, and I have done. The whole current thing about climate change is a load of nonsense. For a start, CO2 changes do not precede temperature change. Temperature changes precede CO2 changes. That's thinking.
It's a really difficult thing to separate out, though, right? Because the historic temperature markers often come down to CO2 and to these oxygen isotopes, and it's a very indirect. It's not as precise of a method as we would hope that it would be.
And that was actually Nir Shaviv's point, where he was like, looking at the physics of this, there's some degree of warming that will be caused by human activity.
Yeah,
but the majority. But what was really cool is his theory was a cosmic ray theory, where he had an electrical theory for cloud formation. And he was like, the ionization that happens in the atmosphere when the sun is weak and cosmic ray radiation is high creates a lot more cloud cover.
And clouds has much more effect than carbon dioxide or anything else. The cloud cover, it's only the last decade or two that people have cottoned onto this.
Yeah, and it's really weird, because if cloud cover is the centerpiece and we're going through if we're going through a cycle, then geoengineering is kind of the only thing that can save the cycle, and that really freaks me out. Where I'm because I was 100% against the idea, where I was like, this is absolutely idiotic.
Well, it's either the savior or worse than we could have imagined in the first place.
So it's like
we don't need to do anything. Warmer temperatures, more CO2. CO2 is plant food. plants grow faster with more CO2. Crop yields have got better over the last few decades. That's a good thing. More people die when it's cold than when it's hot. So warmer temperatures, humans like better.
Why do you think people are obsessed with CO2?
I think they're running a racket.
Go,
I don't know. Yeah.
Well, there's one thing really nice about CO2, which is you can mitigate it really easily, and you can put a stamp on your company that you're a green company if you just deal with CO2. Meanwhile, you're dumping like toxic sludge into the water tables or whatever, and as long as you're like, hey, but our CO2 situation's cool.
I would go even farther and say that in addition to the toxic sludge stuff, you're basically able to even continue producing CO2 as long as you've offset it in a sufficiently detailed manner.
I'm a greenie from way back. I stood for Parliament for the New Zealand Values Party in 1975. Wow. They started up in 1972, one of the first two green parties in the world. And but I've parted ways with them some years back when they started calling CO2 pollution. And I said, CO2 is not pollution. It's an essential part of our life cycle of plants and animals. But if we go down this path, we'll never get off it.
It's worth getting. I appreciate you chiming in, just because it's a topic that comes up over and over, and it's something that I think that people are very what's the word? There's quite a magic show going on, and so it's something worth mentioning, But
and it's like the more that we can talk about it in sane ways, where it's not about saying that there's a sense of conspiratorial agony about it, but we're just like, look, people make mistakes and things become popular in the zeitgeist.
Especially if they're profitable. And it's like, it's not dark and spooky. It's just like, we should probably look at it directly. And I find that most people are very conspiratorial about it. And I'm like, this is the cycle of human nature. I'm sure that you could track the cycle of crazy things that people believe in.
They call, when the temperatures get higher, they call it a cycle, they call it a climate optimum. Right? This is historically what they've called it. After coming out of the last ice age, we had this climate optimum some thousands of years ago. And if you look at all the rises of great civilizations, the Minoans, the Greeks, the Romans, and then the Renaissance, and now they all occur when the temperatures are up.
Mesoamericans.
There you go. Hope for the future then. Perhaps we're not entering the fall of civilization. Perhaps this is the birth of civilization.
No. Yeah.
I like that.
Back to, sorry, didn't mean to derail you with that. It's just it's a hot topic for us.
So it's a good topic. I found this stuff of Dewey's, and there were all these, even before I got there, I'd started to work on the harmonic theory stuff. I'd realized that if you had these sort of musical ratios, I didn't mention, those first four cycles I found turn out, when you multiply them by 4, 5, 6, and 8, you get this 35.6 year figure roughly. So 4, 5, 6, 8 are the frequencies of a major chord in music. And I analysed some wheat prices, and they had all the white notes of the scale plus 2 black notes in them for a couple of octaves. So that was pretty weird. I didn't used to tell people then. I thought they'll think I'm crazy. But I can understand why it happens now, and I don't care if people think I'm crazy. Some people will know I'm not. So anyway, I realised that that this sort of thing happens by nonlinear systems. This was the 1970s, right, when I was first doing this, and then the 80s later. I realised in the 70s you had the Mandelbrot set. And it's based on this very simple equation that produces this whole fancy, very flash mathematical object. If you don't know the Mandelbrot set, I recommend looking it up. It was more computer time was spent on two things in the 70s. One was the Mandelbrot set, and the other one was Conway's Life. And the computers went very fast, so it used a lot of time. But so I decided nonlinear equations is the answer, because nonlinear equations make harmonics.
Yeah, can we unpack that a little bit? Like, the basic idea with nonlinear equations is that you have a feedback element, from what I understand. Yeah, no, it doesn't. It's not necessarily feedback. It's building upon what came before, right, in the series. Yeah, it's I'll give you an example. The first one I worked out, because when I did the wheat prices, one of the cycles is 5.5 years.
and the sunspot cycle is 11 years. So I thought, okay, the sun could be influencing temperatures on Earth. It could be altering rainfall. I didn't know what it was doing, but it was definitely seemed to be having an effect on wheat prices, but making 2 cycles for every one. So I said, let's supposing we got a graph like that, and that's either rain. This dimension is either rainfall or temperature, and this dimension is how fast wheat grows. And so
it's going up and down.
It's going up and down, but when we travel once across and back, we go up and down twice, right? So 11-year cycle produces 5.5. So that's the nonlinear equation, the graph that's not a straight line. So as soon as a relationship between two things is not a straight line, it's nonlinear. And as soon as it's nonlinear, any cycle you put in will produce cycles that are harmonics of the original. So I made a big map of how the planets affected the sun, how the sun affected all these different things on the climate and all the different things around, and how those all affected onto the economy. And I had this big chart. It wasn't supposed to be correct. It was just supposed to show lots and lots and lots of things influencing each other. And if you feed a cycle in somewhere, it's going to produce harmonics. Every step produces more harmonics. But eventually I realized you didn't need all that. It's actually just the fabric of the universe oscillating. Dewey kind of realized that too, because he found that a lot of cycles are synchronized, and some of the cycles on Earth also occurred in the sun. But he said the funny thing is there's no delay. In fact, if anything, the Earth seems to slightly precede the solar ones. And there's a reason for that, is that the fluctuating waves of the universe take time to reach the center of the sun and time to come out again. So we're getting them sooner because of that. Smaller. Yeah, because, we could get them directly. And so what am I looking at here?
Well, I was going to ask, so it's like, so you say that there's cycles on Earth that happen before they hit the sun. Are there similar cycles that you can see in the other planets?
Yeah. In fact, going back to global warming for a moment, it's been observed on other planets and moons that they have been showing temperature increases as well, which rather kind of indicates it's coming from the sun, not from humans.
Wow. Pluto's cooled. Pluto cooled something crazy, like 10 or 20% over the course of a few years when they were studying.
Oh, but Pluto's got a very elliptical orbit, so that will play a big part in what happens with Pluto. Yeah.
Cyclic, though.
That's true.
In my analysis of the planets, I have Pluto in because they hadn't demoted it yet. So you see that in those.
Can I clarify one quick thing really quick? So harmonics, I just want to unpack that term for people who might not be completely aware of it, but the idea of overtones and the idea of reverberations, can you...
Yeah, so if we take a guitar string and we pluck it, it goes like that, right? You can also get it going like that, making 2 waves or 3 waves. And I used to do that sort of thing, but it's not so easy on here. So harmonic is a frequency that is an exact multiple of another frequency. So if you pluck a guitar, because you don't pluck it in the middle and because you make it a sort of an angle shape, when it goes, you'll get all those overtones. So the frequency you're doing, if it was, say, 300 cycles per second, will produce 150, which is half of that, 100, which is a third, 75, which is a quarter, 60, which is a fifth, and so on, all the way down, all these harmonics. And so they're all present there. And usually, as you go to the higher harmonics, the power will drop off.
And is that a result of the fundamental interfering with itself, or what is the mechanism by which these overtones are generated?
There has to be a non-linearity, probably, to have that happen. And so what I found is in anything that's one-dimensional, if you have a non-linearity, you will get harmonics.
One-dimensional here is in terms of factor analysis.
String, I guess.
No, this is in the when the guitar string goes. It's a one-dimensional thing.
I see. Okay.
If you get a drum, it's 2-dimensional, but you can do stuff in 2 dimensions and other things in 3 dimensions. So when we think about the fabric of the universe, which I like to call the ether, but you can call it the electromagnetic field if you like. It's just easier. I find it easier to understand as an ether. When you do that, you've got 3 dimensions. And when you have 3 dimensions, you get an entirely different thing to 1 dimension. In 1 dimension, it's well known that that you make harmonics when you do something. if it's nonlinear. Excuse me. But in 3 dimensions, something else happens. Those waves that are the harmonics become established in their own right with their own structure. And so they can then have the nonlinearity acting in them, and they can produce harmonics of themselves. And so that was my insight that for the harmonics theory. So harmonics theory means, and to state it in the form I usually do, the universe consists of a standing wave which develops harmonics in brackets because of the nonlinearity. And each of these is also a standing wave and does the same. And that's a bit about does the same. This was my insight to how this whole structure forms in the universe. And when you do that, you get out very quickly. You get out musical relationships and tables like Dewey's and so on that people have had as a structure there. And so then the question is, where does it start? These are producing higher frequencies from the lower ones. So it's natural to look up his table. Dewey had a 71 and 142 year cycles as well. But if we start going a bit longer, we actually get up to around 2,300 and 4,600 year cycles, and they've been reported in the climate also. Incidentally, they're also cycles of the four gas giant planets. They produce alignments at that interval as well. So
all of the material. So considering all of the material in the universe, and I think the quantum mechanics. Yeah, I think the quantum mechanics would agree that material is essentially, when we look at the electron or we look at these, what they would call particles, they're essentially talking about these wave functions ultimately.
Sure, yeah.
And so the idea is just that these are subsets of an even bigger vibration.
Absolutely, yeah. So, but when I first of all, I thought that the 2,300 and 4,600 were directly related by powers of 2. But as I got more accurate figures, the ratio that came out wasn't 64. I got 65.05, which was pretty close to 65. And that made sense because some of the cycles, now Dewey must have noticed this, but he never said anything about it as far as I know. There's a 1.11, a 2.22, 4.44, 8.88 year cycles. The sun has cycles of 11.1, 22.2, and so on, 10 times as much or 5 times if you take them the right way. So there's got to be a ratio of 5 in there somewhere as well. Dewey never mentions that. And one of the other strong cycles he found in the most studied cycle ever is the American stock market cycle, 40.68 months he called it, which is 3.39 years. And that one, it doesn't fit into his table either. But if you divide what's one or two of the other ones by 7, you get these ones. So there's a ratio of 5 going upwards and 7 going downwards. It produced more and more cycles that are found in other things. And so I began to work those out, and I realized that this formula I made, it would do things, not just powers of 2. It would do lots of ratios of 2 and a few of 3 and less of 5 and 7 and other primes, much less often. So I started calculating them, and I did it by hand up to 100, and I noticed the music. Then I did it on the computer up to 1,000, and I noticed that there were some particularly strong harmonics. There was one at 34,560. And that's an important one, because then when I started to do it on the computer to higher numbers, now when I was doing this first, we were using computers that were very slow and primitive compared to today's ones. So I did it to 10 to the 20. Next generation of computer came out, I did it to 10 to the 30, 10 to the 40, 10 to the 50. I haven't done any since then. It could be done to 10 to the 60 or 70 now, but it's not really necessary. Those, what came out is this very strong harmonic at 34560. There were other ones near powers of that number, not exactly powers, but near powers of that number. So if we talk in orders of magnitude, powers of 10, about every 4.5, there's a strong harmonic predicted by the harmonics theory. When we look at the structure of the universe, if we start from the Hubble scale, which is the biggest one we can observe, and divide it by that number, now we're dividing both time and distance, because a wave, if it's all light speed waves, say, whatever the relationship is, or in a guitar, when you go to having 2 rather than 1, it has twice the frequency. So you get twice the frequency and half the wavelength, right? So the proportions of the distances and the times all match. So when you do that, the first strong one predicted gives the typical spacing of galaxies. And when you do it again, you get the typical spacing of stars. The next one gives you the typical spacing of planets, then the spacing of moons. The next two, there's nothing obvious. The one after that gives the typical spacing of cells. The next one gives you the typical spacing of atoms and atomic bonds. The next one gives you the typical spacing of nucleons, protons and neutrons in the nucleus. And the next one gives a prediction of quarks, we call them quarks. So I was able to tell people that 30 years ago what the scale of quarks would be. And so all that comes out. Now, at that stage, I knew that I had something that really didn't just do cycles, but also explained the structure of the universe, because there's no theories that from a simple fundamental principle give those structures in the universe. In fact, hardly anyone's even noticed that there are all these structures at fairly regular ratios. That's because they can't predict them or explain them. So that one, at that stage, I knew it was something useful. And I looked at each of the different scales, because within that, the musical structure exists. Those scales are only the strongest points in the whole spectrum. There's a lot of surrounding ones near each of those. And so I was able to do stuff with, like, the galaxy scale. I worked out what the different galaxy distances should be. Now, up till then,
hold on. I want to stop you really quickly, because there's a pretty big spacing variation between galaxies, right? So if you look at the way that things are structured, they seem to be structured in filaments. And so if you look at one way, the distance is small, but if you look at the other way, the distance is orders of magnitude larger. And so in terms of when you say that it's a cycle that is a galactic scale cycle, or if you divide it, you end up with the spacing of galaxies. What does that mean in context of this hugely variable sizing? Yeah. Or if you look at something like the solar system, right?
Yeah, there are. The solar system, there's basically two scales: the scales of the outer planets and the scale of the inner planets. I was going to come to that next. But for example, in the biggest scale structures that's been found, an American and an Australian team decided they'll have a look one each way in space, and they'll measure the red shifts of galaxies as far as they can out. They called it, what they called it? They had a name for it. It's just a thin tube going out a long way rather than doing a wide area. And when they did that, the graph they got showed the number of galaxies at different red shifts, which they interpret as distance, right? And so when they do that, the peaks are like about 8 times as high as the troughs, very clear and very regular peaks. Now, that one is interesting because the distance between the peaks, at that stage, they didn't know what the Hubble, there's a thing called the Hubble constant, and that's the thing that links red shifts to distance, because the distance ladder is a problem, and they've got better and better at this over the last few decades. But at that stage, they didn't really know. And I was able to say that what the value of the Hubble constant would be much more accurately than what they did at that time. And that was because there's geological cycles, one of which is 586 million years. That shows up in the climate and all of that, as well as half it and a quarter and eighth of it. That 586 million year cycle corresponds to the wave that's 586 million light years, right? That these galactic clusters form on. So now I've told this to some astronomers, and they say, "Oh, so you are doing numerology?" And I have to say to them, "Excuse me, you're doing numerology. You've got 586 twice in 2 different units, and you're saying they're the same thing." I said, "No, it's not numerology." I said, "If you have a 586 million light year wave, how fast does it oscillate?" And they say, "Well, you've got to do the formula." I said, "That's right, do the formula. It's very simple. You know, wavelength over period equals c." And they do the equation. Oh, yeah, it is light years, isn't it? Yeah, okay, it's physics. One guy shouted at me a lot of times before I could actually get him to look at it and say, this is physics. So that one, those two are the same thing as far as I'm concerned. This huge...
Can I just point out one really interesting thing about that is that only works out because C is a constant. And the fact that C is a constant, or maybe we can just forget about C for a second and just say the fact that you can make a time distance conversion here implies some sort of density constancy of this medium to me.
Yes, absolutely.
Because otherwise you would have different speeds in different regions and so forth.
It's complicated it's complicated though, because if you say this to somebody who's a physicist, they're like, there's no density.
There's no medium.
There's no medium. Which is why it's really important to think about the electromagnetic field as being an ether type structure, because then you can rationalize these things as being an actual effect of something physical, as opposed to just being like, I don't know, it's magic.
Yeah, and you have a reason for the C to be constant.
Yeah.
Did you know that Einstein, Dirac, Schrodinger, and all these ones always all believed in an ether?
Of course.
Mm-hmm. I mean, Einstein had a weird... We've talked about this on the show before.
It.
Well, he had a weird non-kinematic ether, and so I think that I've thought a lot about this, and what I think that he was trying to say is that it was a responsive ether rather than a directing ether. He was like, it's not a thing that can exert a force.
You can't put a mark on the ether and see where it goes, right?
Right.
Yeah.
And that's the thing. It's something underlying what we observe. It's not what we observe. And I don't care if they want to do it in terms of electromagnetism. You get the same answers. It's just you need more equations. Yeah.
Right. Yeah, we've actually just started thinking about it as the atoms, the atoms in a rarefied form themselves that are actually, so as the atoms move, the ether moves in a radial fashion with them, but that's a topic for a different day.
Yeah. So the same thing happens when you get to the scale of galaxies. There's a number of people noticed, Helton Arp and William Tift, a couple of the main ones, but Fred Hoyle was involved in a few others, that there was this red periodicity, they called it, in red shift of 72 kilometers per second. So if you got a little cluster of galaxies and you looked at all their red shifts, the differences between them tended to be multiples of 72 kilometers per second. Now, if they're really moving in orbit around each other, that's impossible, because they'll be moving at all sorts of directions, at angles to you. You'll be looking across that, so that can't happen. The fact that, as far as I can see, the only way that can happen is if galaxies aren't moving at all.
Whoa.
Can you say more about that? That's that's counterintuitive.
Well, I'm happy for someone else to come up with another one. Well, if galaxies are moving,
the other option, I guess, is just redshifts don't
just away from us.
The other option is that redshifts just don't mean what we think they mean, perhaps.
Oh, they don't. Yes, that's the other option. That's what we're coming to. So, but what I started off with, and I said, well, that looks like about the strongest harmonic before the 34,560 was 2,880. And so I divided that into the speed of light, and I got 104 kilometers per second. I thought, that didn't work. I was supposed to get 72. And for a long time, I didn't understand why that was. And then I remembered Einstein had this velocity addition formula. If you want to add two velocities, you put velocity A plus velocity B divided by 1 plus velocity A times velocity B. And then I said, okay, how many times do you have to add 72 kilometers per second to get to the speed of light? And the answer is, we'll never get there. But after 2880 steps, you get exactly 2 for the redshift. In other words, a ratio 2 in the spectrum of distant objects is divided by 2880. Now, in harmonics theory, 2 is the most important harmonic that always happens. So I said, okay, let's assume this is correct. There's actually be a whole bunch of these things. And I made a graph that showed all of the harmonics out past, you talk about 3, 4, 5, 6, 0, using the simple formula 1 plus z to the power of h equals 2. And so that's the basis of calculating where at those distances, red shifts come back into a simple ratio of the original ones, which means you can get feedback. If the universe is sending energy backs and forwards, then you can get feedback after that. Note that I'm assuming that it can send it backs and forwards. There's time that the universe communicates with itself over long periods of time because it isn't expanding.
So the idea is that the redshift standard separation in these galaxies, is it in these galaxies, among these galaxies? Between us
and them,
is established by feedback from the first harmonic, the octave.
Yeah. And so when I stuck this table on, and I used to do a lot of stuff in the Usenet groups in the old days before World Wide Web started, really. And they were a good discussion forum for physics and cosmology and stuff. And loads of the establishment would all rubbish me, but a few people would listen. And one of the things that I really love is that some of the very best scientists in any area would send me a private email. They wouldn't ever enter the debate. They would read it. They'd send me a private email saying, look up this paper. And one of those ones was a paper by Tift. And he had already, before I put this thing up, published a paper. I knew about the 72 kilometers a second because a number of people observed that. But he had one paper where he says there are other ones as well. There's 72, there's 36, there's 24, there's 18 and 9 and 8 and 6 and 3 and 2.67. In the graph I did, and the list I put, I listed 12 values that should appear. His 12 values that he reported, 11 were the same, exactly the same. The one that he had different was the 2.67 that I didn't list. But when I went to the graph, I could show people it was the very next strongest one, right? So if you want to actually do a statistical test on what he had found and what I had predicted, not knowing about what he had found, it's about a 10 to the 13 or 10 to the 14 probability against that happening.
So do you think these like distance redshift correlations have to do with feedback as much as they have to do with distance itself, or how does that?
It's further down the story where I worked out what redshift really is, and I discovered other people had worked it out. This is the thing. Every time I worked something out, I'd go and look and I'd find somebody else had already had that idea, but it was in isolation. And so it didn't all hang together. But what I was getting it to hang together. So I found the same things at the stellar scale, the distance quanta that fit with the cycles periods found. The same thing in the planetary distance fit with cycle periods, and on down. It's the same at the atomic scale. And I realized all these things have to be the same sort of waves in the same medium. They're all speed of light. They've all got to be in the same medium. And that's why I decided that atomic particles are nothing but waves. And so I put something on the internet about that I thought they were and what I thought the form was. And I got an email from this guy named Milo Wolf. Unfortunately, he's dead now, but he did some very good work. And he said to me, welcome to the club. And I said to him, what club? And he said, the club of people that understand that particles are nothing but waves. I said, oh, good. How many people are in the club? He said, 2 now.
Which is weird because like...
There were 10 within a couple of years. Yeah.
But like if you talk to a quantum physicist and ask them what a particle is and you keep pushing, you'll eventually get to the fact that it's just an instantaneous measurement of a wave.
Yeah.
Right? It's it always comes down to that eventually. And then you're like, what's the wave in? And they're like, it's in the field. And then it's like, you're off to the races, right?
Yeah. So, but a lot of them have this wave particle duality. And even very clever people like, what's his name? Feynman and Wheeler, who are smart cookies. Feynman still finished up saying light is a particle. And it's not. It's a purely wave phenomenon. Everything is purely wave phenomenon. But Wheeler and Feynman got so close because they actually considered the wave nature of an electron. They said there's one wave going out at the speed of light from the electron, and the frequency of it is the Compton frequency of an electron, right? It's going out and making one wave. And then they said there's another wave going out backwards in time, the same sort of wave backwards in time. Now, most of us wouldn't call that a wave going out backwards in time. We'd call it a wave coming in, right? Which is what it is. If you have a wave coming in, when it hits the middle, it passes through and it goes back out again. So it's the same wave after it's passed through the middle. And once you understand that, the obvious question is, how does it know where to arrive, where this electron is? And the answer is, it doesn't know where to arrive. Wherever it arrives, that's where the electron is. That's coming in. Now, a spherical wave, it helps to know that a spherical wave can be decomposed into a whole lot of plane waves traveling from different directions. If you have plane waves from every direction, the place where they have the same phase will look like a spherical wave arriving.
Yeah, and I would push it even one step further and say when you ask what a plane wave really is when it comes to light, it turns out that it's really just a mixture of different helical waves. And so you have a really interesting structure for the ether that starts to emerge. We actually just had Carver Mead from Caltech to talk about this exact situation with the community. He worked under Feynman actually at Caltech, and he was basically, the interpretation that we kind of ended up with was that the atoms are essentially, in communication with one another. Light is actually a conversation between atoms. It's not just this like cannonball that's shot into space or something.
If you take the standing wave that is a particle or a nucleus or something, the wave coming in and the wave going out, if you have an electron jump orbital so that the energy of the atom changes, right, then the wave that's coming in and the wave going out are slightly different frequency. When you actually look at that, what actually happens, you actually get a ripple of this different frequency traveling out from the thing or coming in. And that's what photons are. Yeah. They're just interference effects of atoms. But at the same time, electrons might be interference effects of protons and neutrons, and you don't know where to end up. But the same thing.
The problem fundamentally comes down to confusing an activity, right? These waves are a wave is a verb. It's an activity. Yeah. And you confuse it for an object all of a sudden. You start treating the activity like an object, and now you've got a whole zoo of all of these objects when they're really just motions of the same material.
Which is necessitated by getting rid of the ether. Like there's no way around this, because the minute that you say that there's no ether, which is the material that connects them, then you have to start going in these spooky directions because your model says that there's nothing between them, and so it must be something that's deeply mysterious.
Yeah, and unfortunately people
most
love that
most of them say there's a 0-point field that's everywhere, and stuff like that. And there is. The calculation I get, when you get to very high harmonics, there's this vast sea of not random ones, but sufficiently unrelated to everything that near enough looks like it. When I went to Russia, they said to me, is it 1 upon F noise? I said, yeah. Well, I said, I don't know whether it's 1 upon F or 1 upon F squared. Harmonics theory works the same for both, but it's one of those things. But it's not noise, but it's near enough to that you wouldn't be able to tell the difference. And just these few sticking up above it harmonics that are the strong ones, that are the things we see. There's loads and loads of other energy in between.
Yeah, and I think that that's kind of the tricky thing, which is that I pulled up Tift's 1978 paper, which just to make sure that it's the right one, it is, and now the computer's frozen. But basically he charts all of these different harmonics and he looks at the patterns, and it's called the absolute solar motion and the discrete redshift.
Yeah.
Okay.
Yeah.
And so the looking at the data, right? So I haven't read the paper, but you just look at the pictures and the correlations are pretty noisy. Like it's not like it's a clear thing where you look at and somebody who is just coming off the street and can look at it can easily be like, that's a ratio. It's kind of like it's smeared.
Yeah, I agree.
And I think that's what makes it difficult, is that these cycles are often not clear cut, which makes sense, because if you look at a wave that is a pure wave, you'll have something that's really neat and clean.
These lovely sine shapes,
But the minute that you have a bunch of cycles that are adding up on top of each other, you're going to get stuff that's really hairy and by necessity smeary.
Yeah.
And so
and yet he managed to extract all those things, and they agreed with what I had predicted separately from him.
Yeah, and so that's the thing, which is like, if somebody's looking at it super, super closely and is devoting an enormous amount of time to seeing what's there, they can create the correlations, but it's also easy to stand there and to be like, I don't see it, and I don't think that it's there.
And Tiff faced that problem all his life. And his papers were all published because when they gave it to peer review, they couldn't find anything wrong with them. So they all got published. But the editors used to write notes. We don't think this is right, but we can't find anything wrong with it. So we're publishing it. You can find something wrong. But some of the ones he did 2 systems that he used as a reference frame. One was the center of our galaxy, and the other one was still relative to the cosmic microwave background radiation. And in either of those, the whole sky shows these 72 kilometers per second shells, right, over the whole sky. And you can actually tell that you're at rest because of that. But there's 2 rest frames, it seems. One is our galaxy and one is the cosmic microwave background.
Yeah, what do you make of the cosmic microwave background?
Well, the first person to correctly predict a temperature for the cosmic microwave background, he wasn't trying to do that because he didn't know there was such a thing, but it was Eddington. And he said, if you calculate what would happen if all the stars light, it may have been related to Olber's paradox. If you take all the light of the stars and it sort of gets scattered by dust and done all these things, eventually, where does it end up? And the answer is it ends up at about 3 degrees K. The first people that were the Big Bang ones, when they first predicted it, they predicted 50 degrees K, right? That's how far out they were. And then they found excuses and reasons and stuff to adjust it all to get to 3. But Eddington got that number. He didn't have any better facts than them, but he got that one. So I suspect Eddington was right, that it's Eddington got a few things right. He did a couple of wacky things as well, so he's not looked up that much. But him and directed the large numbers hypothesis, which also is well worth looking at to understand the large-scale structure of the universe.
Mass luminosity, he also nailed that one.
Yeah, I'm frantically looking up the large numbers hypothesis.
Yeah. Well, there's 3 numbers.
Okay.
They misstate the definition of one. They state the age of the universe and the time that light takes to travel across a particle. Now, I think that's a silly way to put it. I think it's the size of the universe compared to the size of an atomic particle, right? But because they believe in the Big Bang, they think the universe is expanding, so they can't do it that way. So that's one. Another one is the strength of gravity compared to the strength of the strong force. And they're both of those are around about 10 to the 40th. And the third occurrence is that the number of particles in the observable universe is about 10 to the 80. So it seems too much coincidence. You've got these 2 10 to the 40s and this one 10 to the 80. You can get it down to 1. When you understand the wave nature of a particle, if you go out a distance 10 to the 40 times the particle's wavelength, then the sphere that you will have has got a surface area of 10 to the 80 times the original size of that thing. So now what happens? If the particles are talking to each other, if the outgoing wave of one particle becomes the incoming wave of another particle, which is the only way you can recycle the energy, then at 10 to the 40th distance, they become the incoming waves of other particles, and that's the distance to which we can see. We can't see further than that, not because the universe stops, but because protons and neutron waves are all become the incoming waves. So we can't see ones further than that.
And relative to that distance, how far can we actually see at this point? Like relative to the theoretical limit of what we should be able to see, how far can we see?
With the new telescope, they are pushing right up against it.
And so what have you? I don't know if you've been following the James Webb at all, but the appearance of these kind of fully formed galaxies super early in the universe. Yeah. What's your take on that?
Well, I expect that. Big Bang Theory doesn't.
Yeah. What's your alternative?
I think the universe is much older.
Yeah. So can you walk us through your cosmology?
Yeah. Okay. So having got a lot of cycles from the range of about a week. Now, there are shorter cycles that I know, but it doesn't work for those. But from the range of about a week up to 586 billion years, I took the common cycles I knew that had good periods for, and I stuck them all down in the computer. And then I took the pattern predicted by the harmonics theory. And if you put them on a log scale, then you can just slide them past each other and see where they match. And as you slide them past each other, I started at 1 billion years because I figured it's got to be longer than that. And I went upwards. And when I got to 10 to the 23, 1.4 times 10 to the 23 years, there's this massive spike sticking up. And there's a little structure around it of other ones that are ratios 2 and 3 and 3/2 and stuff. But basically, the answer is very, very clear on that the size of the universe is 1.4 times 10 to the 23 light years, which is 10 to the 13 times the Hubble scale. So those steps that I'm talking about, Hubble, galaxy, stars, planets, it's 3 more steps up from there.
And so what does that imply to you? Like, so...
Well, that implies they haven't gone big enough yet. Every so often we've got to increase the size of the universe, don't we? You know, it's a scientific tradition.
Well, it was. I mean, I'm always shook by how the Milky Way was the extent of the universe at Eddington's time.
Yeah, in the 20th century.
Yeah. So it's like we've increased the size of the universe dramatically in the course of the last 100 years, and I'm not sure that we're done with the expansion. Yeah. So okay, so in your cosmology, you say that there's no such thing as the Big Bang. So do you have an eternal universe? Yeah.
Well, I don't know. I can just tell you about one other coincidence. This is maybe not quite in your down your line, but I did the Vipassana meditation. And I heard about the Buddha and some of the things he said, and I started reading some more. And someone asked him, how you say there's cycles and these long cycles. What's the cycle of the universe? And he said, if you dig a hole 7 miles, they use the units of the day, I can't remember what they are, 7 miles by 7 miles by 7 miles, and fill it with sesame seeds. Then you take one out every 100 years. When you're finished, that's the cycle of the universe. I said, sesame seed, I'm going to call that a millimeter. Did the calculation, and I got 1.4 times 10 to the 23 years. Same as what I got. So he knew something.
So hold on. I want to clarify that. So what you're saying?
How he did that.
So what you're saying is that you went through the Buddhist text, and you took the sort of the sage wisdom of the Buddha, calculated out the number of the years that you would get from that process, and arrived at the same number that you got from this log comparison. What was the data that you were doing the log comparison of again?
It's all the common cycles that Dewey had found. So there's loads of them in the range of a year to sort of 100 years. There's lots and lots there. There's a few shorter ones as well, and there's some longer ones. So the longer ones included the sort of light years to the nearby galaxies and the scale of these very large structures and that, and the geological cycles. There's a number of cycles in the sort of 100,000 millions of years in the solar system, and take those ones as well. Yeah.
But you were saying that you said that you took 2 of them and you slid them past each other. Yeah.
So on a log scale, because on a log scale, they've got to match at some point, if the theory is correct. So when I slid along, when I got to 1.4 times 10 to the 23 years, then I've got a CSV file on my website. If you go to ray.tomes.biz, you'll find listed somewhere at the bottom a CSV file, and that's got the strong harmonics. It's more than the main line of the very strongest. I don't put the whole lot in because there's 10 to the 50 of them. I put the relatively strong ones in any range. And if you get that CSV file, you can see the harmonics there. And
I'm just trying to understand. I'm kind of dense when it comes to this the visualization of charts, and so what I'm just trying to understand is you're saying what is the process that you're doing where you say that you put it along the log scale and you suddenly get this thing that jumps out. Like I don't understand you have a list of different periodicities, right? And so what are you graphing?
I start from 1 billion years and I go up sort of like 0.1% per time, right?
I'm not sure what you mean by you go up by 0.1%.
I start with 1 billion. I keep changing it by a tiny bit, and then I see if that was the cycle of the universe, how well would that fit?
I understand.
The pattern of ones that are observed.
I get
right?
it. So basically, you have a pattern of observed distances, and you're like,
Yeah.
if the fundamental harmonic is 1 billion years, then
Yeah.
how does it align with the pattern that's measured? And what you
That's
do
right.
is you continuously increase this
You can
harmonic,
see how it fits.
and you set it upwards and upwards, and eventually, when you get to
Yeah.
1.4 times 10 to the 23, that is the harmonic that appears to fit perfectly with the observed cycles.
Yeah. Now, there's a couple of interesting things that come out of that. Dewey had a lot of those, the table of ones that were proportions of 2 and 3, right? And I had added to that the ones that were divided by 7 and multiplied by 5. I'd included a lot of those ones in. And it gets all those. But one of the fascinating things is one of the cycles that had not been put in is there's a cycle in the Canadian lynx of 9.6 years. And there's a bunch of things that are found to have either 9.6 or 9 2/3 year cycles. So let's take the average of those and call it 9.63 years. It comes out and says there should be a strong cycle at 9.638 years. So it says that cycle should be there. Now, that's a confirmation that what's being done isn't some sort of silly thing, and it's finding something that's real that does correspond to the universe we're in.
So, given that it is real, right? So there's, I think that it's a difficult thing to accept as real, but I think that for the sake of discussion, like assuming that it is.
Yeah.
How can we? My instrumental mind immediately goes to like, how can I use this to my advantage? How can I use this to my advantage, Ray?
Well,
even in terms of understanding the universe.
Money.
After I worked that out, I wanted to buy a new house, right?
Mm.
And there's a cycle. You don't need to know all of that. You just need to know there's a cycle of 7 point something years, and the cycle of in the house prices. It's different in America. It's 18 years. You get that, and you look at what they're doing, and you say, "There's a good time to buy." Apparently, there's the two families, the Rockefellers and the Rothschilds. One of them used the 40-month cycle since the 1800s, right? And the other one used the 18-year cycle in real estate since the 1930s, when the Empire State Building was built using the cheapest possible labor. And those families got rich using cycles. So that's how you do it.
Interesting. Okay.
I have a really far out question that I want to ask for my friend Doug. Can you make a marker for this? Because I want to send this to Doug. This is really interesting. Do you think, so if matter, if atoms are just one frequency, one standing wave of this universally pervading material, this fiber of existence, are there other frequencies of experience? Is it possible that there's structures we can't see because they're overtone structures, and that there's whole levels of conscious? I mean, this is just getting into the
Doug, we love you.
Complete weeds, but I want to hear your thoughts on that idea.
Oh, okay. The other people that I talked to recently were Laura Lee. Do you know Laura Lee?
Mm-mm.
Oh, okay. What's their institute called? It's got a funny name. I can't remember it. Anyway, we went into that because you were more on the scientific side and they were more on the meditation and other side. Yes, I do think so. When you do all of this, I've talked about the speed of light of all these waves. But when we have an atom, most of the mass is in the nucleus. But if they bump against each other, it's a much more spongy thing, which the electrons and stuff consider to bang against each other. I call it the atom wave.
The shell, maybe? Electrons. I don't know. The shell of the atom? They
bump each other. So the speed of sound is those waves bumping together, but because the inertia is coming from the nucleus, but the sponginess is coming from that. If you bang a bunch of neutrons and protons together, a wave will travel at the speed of light. But with these, it travels much slower. Now, in the harmonics theory, you've got both the frequency and the distances show this harmonic structure. So if there's these sort of ratio 34, 560 and near powers of that, will that show up as velocity also because it's distance over time? And the answer is yes, it does. When you do that, the speed of sound, if you divide the speed of light by that number, you get about 8 kilometers per second. That's very typical of the speed of sound in solid materials, right? If you divide it again, you get, I'm not going to do these calculations in my head, but you get a bunch of other ones. Each time you divide it, the second time you get the speed of heat. Now, we don't normally talk about the speed of heat. It's also the speed of nerve impulses. One of the speeds of nerve impulses, there's multiple of them. If you divide it again...
Because the speed of heat is pretty specific for substance, as is...
It varies widely, yeah. So if you take lots of them, in any of these areas, like if I take the speed of sound and lots of different materials, and I analyze it by what I call Kotoff's method, it's looking for values that are fractions or multiples of the other values. And when I do that, I get a couple of specific values out for sound that do have the sort of ratios you expect in harmonics theory. You get the same. You can do the same thing with heat, but heat, it's got a wider range. Then you get the next one is the typical speed of ocean currents. The next one gives you the typical speed of continental drift. So we're now down to a centimetre per year, right? And those things are at those ratios. And if you have a look at them, you've got the old elements that they had in ancient times: earth, continental drift, water, ocean currents, fire and air and fire, and ether. You get these 5 levels, and they show up. And if you make a diagram, I've got one that I put 5 lines horizontally corresponding to those velocities, and along the top I put the distance scale of all these structures in the universe, and then I run diagonals. I make it into triangles of 60 degrees, and one of those sets of lines gives you period, and one gives you distance, and that way it gives you velocity, and the 3 are obviously related. There's only 2 dimensions. And when you do that and start to do things like, for example, Jupiter goes around the sun in 11.86 years. Now, 11.86 light years happens to be one of the distance quanta that you find amongst the stars. There's multiple of them, 4.44, Dewey's 4.44. It actually comes out at 4.43, so it agrees very well that the stars like to be that far apart. So then when you do that with Jupiter, but Jupiter's doing that period around the sun. So it's moving at sound velocity. It works out when you work out its velocity. It's a typical sound velocity one. So it falls on that second line down. And you can find these connections. And these connections, I call it the universe wide web, because each connection, you've either got a common period or a common wavelength. If either of those is in common, the things can interact, right? Because the particles at the nodes of the things are interacting if they're in the same places. If they've got the same period, they can interact. So you can see methods of interaction that aren't normally recognized with the structure.
So doesn't that imply that, okay, so if you have a universal harmonic breakdown, that everything comes from the single harmonic that's at 1.4 times 10 to the 23 light years, then
yes, yeah.
Could you have a parallel one that's happening in the background?
Different? Yeah, you could, but where I was heading with that is those ones, they're, yeah, okay. I do Vipassana meditation. One of the things that happens when you do that, you start observing your breath. You shouldn't try to do this. These are not instructions. You should go on a Vipassana meditation course if anyone wants to do it. Then what happens is you spend a lot of time observing sensations throughout the body. After you observe them a lot, various energetic knots and things exist, and they dissolve if you do it right, which is to observe them with equanimity. Not wanting it to change, not wanting it to not change or anything. And these things begin to dissolve, and you begin to become aware of finer and finer, what do you call them? You can call them realms. Some people call them realms. Finer realms.
Overtones of experience?
Yeah, they are. These are the realms that in Buddhism they describe as the human realm. There's 5 more realms below us, and there's 31 altogether, and so there's where the different devas and the what are the next ones up from devas? the Brahma,
Don't know.
Brahmas,
Higher powers. Yeah, I don't know. Higher spirits.
Yeah, and that changes. These things get finer and finer, but there's one point where it actually changes its nature as well. They call them fine material and something else, planes. You can experience
the
these things for yourself.
immaterial world, the fine material world, and the sensuous world.
Yeah, that's right. Yeah.
Okay, so
I think you can find that structure in there to some extent in those levels that I'm talking about.
Oh, that's really interesting. I mean, I do think that training awareness and being able to become progressively more sensitive to things does expose you to pieces of experience that other people don't get, right?
Higher harmonics.
You know this, that it's like if you, in science, if you have data and you're looking at the data, you will find something. If you're just collecting data and you're not looking at it, then you're not going to find anything. Like that's a naive truthism, but I think that is the case, that as soon as you start to look and to pay attention,
you start to impose your own order. Yeah.
And that's the foundation of the sciences.
Yeah, like Tiff did all this work, which I regard as really, really good. Then him and another guy got a theory. And after that, he stopped finding those things he'd been finding, and he started finding some of them and these other ones that fitted his theory. And I think that that's what he was looking for then. Now, I don't know I'm immune from this myself, but I try to be. I'm aware of it, and I try to be immune from it. And when I make a mistake, I try to recognize it. So, like, I went 2 years down the path with the wrong calculation originally of harmonics. And then I realized that this didn't do, when I got the 65 thing, I realized it's not right. And that was the other method. And so I had to go back and start again from that. You've got to put that aside. You can't get your ego mixed up with your theories, If you can't do science that way.
Well, it's hard to not do that when your career depends upon it. So you're in a particularly unique and perhaps because I retired, I had enough money, I could do this research, and I didn't have to answer to anyone. But when I talked to American professors in that, they weren't very interested. When I went to Russia, they had a very different attitude. This was in the 90s, right? And I asked them, why is there this big difference? And they said, it's a tenure system. You've got to do incremental knowledge, in the to keep your tenure. And they said, our system's changing and ours will be like theirs in a few years' time. It'll all be gone, the ability to think freely. Yeah.
You said that you worked with an incorrect set of calculations at the beginning. How did you change your mind about this?
Yeah, well, it basically that came out with most people when they start looking at powers of the musical relationships and the powers of two over large scales, keep going powers of two all the way as the important ones, and they have the musical notes running off that. And that was what happened. But it didn't fit. It didn't fit the data, so I knew it was wrong. You can't try and make it fit the data. You've got to make the theory's got to, the data's right. The theory, I quite often get people in physics telling me, your thing is wrong. And I say, why? Because it's this and this and this. I said, that's your theory, isn't it? Yes. I said, I'm not trying to match your theory. I'm trying to match the world. And a lot of them have trouble with that because they think that their theory is the laws of the universe. Yeah, it's not. And I don't think mine is, but I think it's an important step towards it.
Mm-hmm.
That's worth mentioning. There's, I found a diagram in a book by John Gibbon. Now, John Gibbon did some clever stuff, but he made a couple of mistakes and he went out of fashion. But he had one very nice diagram I liked, and it put, in one direction, it put mass or energy, and in the other direction, it put wavelength or period, whatever you want, wavelength or diameter. And when you do that, it turns out you can't go everywhere in this diagram. There are two diagonals in it. One of them is the limit from black holes due to general relativity. You can't go past that. And the other limit is the quantum limit, and it runs at right angles to the other one. That's one of them's running, if we say a triangle, there's a point on the left, a point up, there's a diagonal running up to the right, there's a diagonal running down to the left. That's the quantum, and that's the general relativity. At the right-hand side should be the size of the universe, which we all had wrong to start with. And then I realized it's got to go a bit further right. And so that gives you the general relativity works off that and works well near that diagonal. quantum mechanics works well near that one. Harmonics theory works right across, but it's more of a ghostly thing. It doesn't say it has to do this. It just subtly influences it all, I think. And I think that a proper ether theory can combine all three and do that. And I've got a couple of clues I can offer because I'm getting old, and there's parts of this I'm never going to do now because my brain's not that good anymore. When you get to the particles, they divide them up into a number of categories. There's the electron and its lot, which we'll call one. There's the mesons, which are supposedly made of two quarks. We'll call them the two. Protons and neutrons and all of those big family, which are threes. They've got three quarks. And they've made a couple of other ones. They've got pentaquarks and other stuff now with more. But I think those numbers 1, 2, 3 are actually the number of waves around the equator of the thing, right? The electron doesn't. That's the only one that's been solved, by the way. Milo Wolf solved the equation for the electron, so that's known. And
is that
works.
different than the wave equation for the electron?
I don't know.
Okay, fair enough.
I don't try to follow quantum mechanics.
It just doesn't seem that different, honestly.
Particle physics is well, I can tell you because Feynman and Wheeler actually have in their book a thing where you imagine the whole universe is filled with the ether, and just to make it easy, I think of it as like jelly, which you guys call jello, and you put a sphere in it, right? And you get the north and south pole of the sphere, and you rotate it 180 degrees, and then you spin it. Now, it's taking the jello's joined to it, so it's got to go around as well, but you think that's just going to rip it to shreds, but it doesn't. What happens is it goes around like that and around like this. It goes under, over the thing. And after 2 rotations, it's back to where it started. In other words, it's a spin-half particle. So the spin-half particle. Now, Feynman and Wheeler were aware of this model and of the spin-half. Milo Wolf proves that model is the electron. You know, it does work. It does everything. Every property of the electron comes out of that. I think that the equations for the proton and neutron are going to be much more difficult, but I think trying to add extra dimensions to reality and all of that stuff, that's totally unnecessary. I think you've got to do it using a simple nonlinear equation in the ether and work out how do you make it spin around with 3 bits and do that, and that's how to do it.
Yeah, we did an animation of this actually for one of our other channels, which everybody should check out. We'll send it to you later. I think you might enjoy
great.
it. Yeah, the spin 1/2 is an awesome little puzzle for the material science of the atom.
Yeah.
Do you have anything else about that? Because I have something really far out that I want to ask you. We've been talking to some archaeologists lately. And there is a cycle in Mesoamerica that's driving me absolutely nuts because the Mesoamerican civilizations had a solar calendar. They also had this 260-year calendar, which
derived from Venus, is it?
No, I mean maybe you're right. You're right. That's very close to like the visible portion of Venus's, which I think is like 256 or something like that.
Yeah.
But I wondered if you'd thought any about that because it coincided with the solar calendar every 52 years, which is a huge holiday for them. And I don't know if you've given any thought to that.
I've looked at some of those ones, Aztec and stuff ones, and they did use Venus, and it does this lovely dance with the Earth every 8 years, you know, and it's very interesting stuff. And I can see where they liked it. Venus is a nice bright thing in the sky, next brightest thing after the moon. And I like all that stuff, but I haven't found any real connection with the cycles that I've studied. But the 600,
Venus it is.
Yeah, it's
600 years.
Days.
Oh, is it?
Yeah.
Okay. Well, 263 days. Okay. Still not quite.
Well, it's an average.
You said 600 years, right?
It's different. Well, say it one more time.
You said 600 years, right?
No, so it's 200, and they have a...
no, the other one, the other cycle.
It's 52.
52, yeah.
I believe 52.
I thought you said something about 600 years at one point.
I'm
No.
I'm not sure. I don't think so.
Oh, okay. Well, can I mention 600 years? There seemed to, at one stage I thought there was a 600-year climate cycle because people had said that, but it doesn't actually seem to be a very strong one. There's 355 and there's 207 and there's some others, 510. But it does seem that the ones of that order do give the rise and fall of civilizations, that you get civilizations when the temperatures are higher. But there is a 600-year cycle. If you go back about 1200 BC, there's a fellow called Moses, right? And then you come to about 600 BC, there was the Buddha, there was Lao Tse, Confucius, and Zoroaster most made an appearance about then. Then you get around naught, you get Christ, and then at 600 you get the other fella, Muhammad. At 1200, there were a couple of revisions, but there doesn't seem to be anything new. And in the 1800s, there's about a whole host of different religions started up around different things. So there does seem to be a 600-year cycle in religions. If you want to start a new one, the next best time is the year 2424.
I was just thinking that. I was like, we're in the clear for at least a couple hundred years.
yeah. But there's some other interesting things relating to that. At one stage, I was making a little chart where I put for every one of these 3, 4, 5, 6, 0 ratios, I'd go along a line, then put another line underneath for the next one. And I was doing all the different intervals of different things. And I had the 600-year one on it for those. So I look at if you divide that by 3, 4, 5, 6, 0, multiply it, what you get. When you divide it by that, you get, I don't know what you get. You have to do it twice. Somewhere along the way, you get to a weekly cycle. How have I got that hooked up? But there's a pattern of weekly people go to church, and this is when they get new saints. And then a seventh of that is a day, and the seventh of that one is about a lifetime. And then when you divide that by something else, you get things that match, like you get brain waves and cycles that are the nearest thing to thinking things in the economy, and the whole thing does seem to match up. You can make patterns there, and it may be just finding patterns that aren't there, but there do seem to be things, and you can go several layers. One of the best ones I got that went multiple layers, in the solar system, you've got the outer planets that are on this 80 and 160 minute light minute waves. The inner planets are on 3 and 6 minute waves. The outer planets are made of hydrogen and helium, and so is the sun. Hydrogen and helium atomic masses, 1 and 2 are hydrogen, and 4 is helium. Right? If you have a star that finishes burning all its hydrogen, the next one it goes to is 12. It makes carbon. What's his name worked out, and didn't get a Nobel Prize for, Fred Hoyle. Now the inner planets, they are on these 3 and 6 minute waves, which are a 14th or a 28th of the outer planet waves, right? What's the Earth made of? The atmosphere is mostly nitrogen, which is 14. The crust is oxygen and silicon is 28. The core is iron, which is a mass 56. Masses are, according to Planck, related directly to frequency, right? The frequency of those particles is that. So now that's actually 6 of those big steps of 3, 4, 5, 6, 0 from the scale of the solar system to the scale of the atoms, and you're still seeing those planets on the same scale as the particles they've got match their orbits, and the outer planets' particles match their orbits on that scale.
That's interesting because for astronomy, not I guess astrophysics too, is that one of the biggest challenges is looking out to be able to figure out what something is made out of. And you have to depend on spectroscopy because you're waiting for it to pass in front of a sun so you can look through its atmosphere. But it would be really cool to look at some of that data as people are trying to figure out what the things are made of, to see if that correlates to what the cycles theory would predict. That'd be really interesting.
I need to do another one. I did one with some of those when they didn't have enough. But they've got so many. They've got thousands of planets now, haven't they? So I should put those through the my Kodov method one and see what comes out of that. Be interesting. Yeah,
that'd be very cool.
Yeah.
I mean, there's so much here, and I think that it's best to dive into these things a little bit at a time, so that you have the opportunity to go into the world and to see how it fits and to start looking at things. And so, for people who have listened, what do you and they're interested in being able to tease these things apart, how do you suggest that they go about it? Like, how can people pursue this? Because it's not a conventional. You can't go to university for it. So what do you do?
No, well, you can go to university. I've had one person once ask me advice to how do I do this at university? And I said, okay, make sure you include some of the maths of it. They wanted me to sort of be a guide for them, and I declined, which I realised later was a mistake. I should have said yes, because they might have been the person that takes over from me when I kick off. So anyway, I would say look widely. I used to go to the library and read. I'd go in the geology department, I'd go in the astronomy department, I'd go in the biology, I'd go in the economics, I'd read anything I could find on cycles on any of them. And that's how I gathered my stuff until I found out about the Foundation for the Study of Cycles, and they had a big library. Unfortunately, the Foundation for the Study of Cycles had a couple of hiccups, and they lost all that library.
Oh, wow.
And they were reformed some years ago on a proper footing, and it's going very well now. Again, they've got a board of directors, and they're bright guys, and they're all in the financial area. So I'm the science guy, and my job is to try and get more scientists that are interested in. In the old days, the foundation had an astronomer, a geologist, agriculturalist, and a climatologist, and all these. We want to get back to that. And there are people that publish in those areas, but it seems to be a dying thing. Not so many young ones doing that. So it's good. It would be good to get some young ones publishing in those areas. And to that end, I do have some funds available for people that want to study. It's interesting because I list 3 things related to Vipassana meditation, and then I list 3 things in my charity. The first one is related to harmonics theory. The second one is related to cycles, really. That's interesting studies in that. And the third one is called demystification of science.
Yeah, we'll take some of that money.
So you guys are doing some of that. So I should send you something. You're doing it already, so I'm not going to send you as much as I'd send someone who's going to start a career in it, right? Because I'm trying to get new things happening. Well, we are supported by listeners, and it's pretty awesome. And all the money has gone right back into the show. We're doing some travels this winter. We're starting to make friends with a lot of the people in person that have been on the show, and we're gonna eventually be able to do this as a live stream. And it actually does matter a lot. I just want to say, not for you necessarily, but just for anybody who's listening. If people want to just give a couple $, it really does add up, and it really is allowing us to do some incredible stuff.
Because I think that the goal is to grow this into something that is much larger than just a podcast, right? So this is the way that we're meeting people, and we're finding the ideas that are most interesting. And I think that down the line, that what it's going to evolve into is, in my ideal world, it would be a research institute. I want to bring together the people that are interested in these questions that can't find funding other places, and be able to serve as a clearinghouse for funds for people who are working on projects, so that they can get published and they can contribute. Because it's you said something interesting about the science in the Soviet Union and how it was changing in the aftermath of its collapse. And there is a calcification of institutions that occurs over time that you have to realize that is part of what an institution does.
It has a life and death.
It has a life and death, everything else. There's a cycle.
It's time for some new institutions.
When they asked the Buddha, he said, all compounded things eventually pass away. And they said, "What about your teaching?" "Yes," he says, "that's the same." And apparently at that time, some of the monks predicted that it goes in successive 500-year intervals where it decays away, where the level they call wisdom is there, and then concentration, and then something else, they pass away, and then morality, and they pass away. But he predicted there'd be another one 2,500 years after the Buddha. And the teacher that I follow, he started teaching in the 1950s, which was that time. And so we've got 500 years of a pure teaching, and then that starts to die away again. And then you have to wait for the next Buddha, and they are very, very far apart.
Oh, well, if you said 2,500 years,
yes.
we're right. I just looked at now, and Buddha lived 500 BC, so we're just about due.
Oh, we are there. Yeah, but you'll find two different dates for the Buddha. All the Westerners use one set of dates, and the Buddhist countries use a different set of dates about 80 years earlier. I don't know if one got mixed up with his birth or his death, but so I use the ones that I figure the Buddhist countries ought to know best.
Definitely, yeah. I mean, it's really fascinating. I think that the more that we can realize the interconnected nature of things and the way that we want to be able to change the world, and we want to be able to say that we have an influence on the universe, but there's almost a certain reverence. There's a certain spirituality in being able to look out and to recognize that you are a mote of dust in the vibration of the universe rather than being a god. Yeah. And we spend a lot of times being able to harness... Oh, go ahead.
No, okay. I want to go and give a couple of quotes here. But first of all, on the subject of you starting an institute and getting people in to do things, about how much do you reckon you need for one person for a year to be doing studies there? Roughly what?
That's a really interesting question. I mean, there's been a lot of research about what sort of salary actually makes for a reasonable life. Depends also if they're doing experimental work or theoretical work. I mean, it's obviously extremely expensive to employ people.
Yeah.
So
but
I don't know.
Let's say PhD students or something like that, they don't need as much, do they?
Yeah, if they're working on like a part-time basis or on a small project, I don't know. You could probably offer them peanuts and they would do it, honestly.
Yeah. Because I would like to explore with you the possibility of me offering one scholarship each year for someone, or maybe for several years.
That'd be really amazing. Yeah.
Now, I've got to bring up some quotes.
Let's hear them.
So this is Edward Dewey. Insofar as cycles are meaningful, all science that has been developed in the absence of cycles knowledge is inadequate and partial. Thus, if cyclic forces are real, any theory of economics or sociology or history or medicine or climatology that ignores non-chance rhythms is manifestly incomplete, as medicine was before the discovery of germs. Now, I love that, because that's true of all of those fields at the moment. They're not taking account of the cycles, which are cosmic forces affecting us. And just to give you another view on the same thing, Krzyzewski...
hold on, before you go to that quote, I want to add that there is... that perfectly lines up with something that I've been realizing lately, which is that to treat the models that exist as purely wrong is foolish. You have to treat them as incomplete.
Yes,
because
sure. Yes.
There's some boundary condition where what has been described and worked out is accurate, and all that you have to do to really make it snap into place is make the theory more complete. And I think that that's a really brilliant point. And I also love the humility, where he's not like, I'm the greatest scientist in the world, cycles are 100% real. He's like,
or 100% of everything.
Or 100% of everything. He's like, if they are, then we must consider
real.
them, which is just like, that's a lot of humility.
He was a careful man with all that stuff. This is a Krzyzewski one. Life is a phenomenon. Its production is due to the influence of the dynamics of the cosmos on a passive subject. It lives due to dynamics. Each oscillation of organic pulsation is coordinated with the cosmic heart and the grandiose whole of nebulous stars, the sun, and the planets. This is much more poetic, but it's also very scientifically accurate. So we're the passive subject, by the way. We're the passive subject. We're just dancing to the tune of the universe.
It's funny because the ancient astronomers are obsessed with that. Every last one of
the
them.
Hindus have known that for a long time. No, the Indians have known that for a long time, haven't they?
But even like Robert Hooke or Huygens or Newton, these people were very keen on the musical relationship of the heavenly bodies. It was somehow, it was an indicate. I mean, they took it very religiously, of course, in their cultural context, but it was very much a guiding light in what they were trying to make, how they were trying to make sense of what's going on out there.
Yeah. Now I've got a couple more here. That's not it. I'm just trying to find, there's a couple more Dewey ones which are worth doing. Where are they? I've got too much stuff here. I'm searching the pictures of them all to try and find the right graphics. Here we go. So this is in the case for cycles, so I recommend people to download that. There is considerable evidence that there are natural environmental forces that alternately stimulate and depress mankind in the mass. These same forces may also affect plant and animal life, weather, and even such normally unchanging things as chemical reactions. Now, that's interesting because the Russians have done a lot on that. There was an Italian named Picardi who did a lot of study of chemical reactions changing depending on cosmic influences. If he went underground, it was different to on the surface and so on. He did a lot of study. And the Russians took that further, and they found it applies to atomic decay as well. There's another one from Dewey. The argument for the existence of these forces runs something like this. Almost everything fluctuates. Many things fluctuate in cycles or waves. Many of these waves are spaced very regularly and have other characteristics that indicate that the spacing cannot reasonably be chance. Non-chance spacing must, by the meaning of the words, have a cause. This cause must be internal, dynamic, or interacting, feedback or predator prey, or external. In any event, it must be a force of some sort. In many instances, this force cannot reasonably be internal or interacting, therefore presumably is external. I think he came to that reluctantly, and this was the advice he got from Feynman, who was a great physicist. I'm indebted to Professor Richard P. Feynman, theoretical physicist of the California Institute of Technology at Pasadena, for the basic structure of the article. Professor Feynman once said to me, in regards to cycles, the proper scientific assumption to start with is they are chance. If they cannot reasonably be chance, the next assumption should be they are caused within the phenomenon or the system of which the phenomenon is an interacting part. Only if the cycles cannot be a result of chance or endogenous causes should we undertake to postulate external or exogenous causes. This formula of Professor Feynman's has constituted the basic philosophy of the foundation from that day to this. It is the framework around which the following paper has been built. That's the Case for Cycles paper. And I should mention that the guy that's running at the place now, Richard, names keeps coming out of my head. Anyway, the man who's running it now very much believes in that philosophy of Dewey and is trying to recreate the whole thing because we're trying to get it back to where it was when Dewey was around, and then we can go forward from there.
I love that. That's beautiful.
That's awesome. I love your work. It's really stimulating in terms of all the possibilities for, like, just bleeds into every single aspect of everything we study here.
Yeah, it's cosmic and it's beautiful. And science is rarely beautiful, but I think that this is a beautiful theory.
Yeah, it is. A couple of ones that come to mind is one of the great physicists was asked, what are you guys really trying to do? And he said, we're trying to work out a formula that's small enough to fit on the front of a T-shirt and explains everything that happens in the universe. So I put his quote on the back of a T-shirt and I put what I thought might be the formula at that stage. It might be, I don't know if it is or not, on the front of a T-shirt, and I had that. It didn't get that many questions. I've got a couple of other T-shirts to get more comments.
Maybe we'll make one of those one day.
Mm-hmm.
Yeah.
All right, Ray, it's been, it's been so dense. I want to step back and process some of this stuff, but maybe we'll get the opportunity to talk to you again down the line.
Yeah, I'd like to do that. Let me just check my little list here to see if I mentioned the things I should have.
Last chance.
No, I think we did cover most of them.
Nice.
Yeah.
Very good.
There's a lot more. I've been making a chart. It looks like this. You won't be able to read it, but you can get the idea that there's a lot of words on it. And each word is one area of study for one person who did some study. And I want to make it so that I have several overlays, one of areas of study, one of specific stuff, one of people that did studies, and show how they all sort of link up. And I'll do one in each color and have them so people can pop which one they want to the front as an idea.
Cool.
So that people want to go further, because some people will have an interest in just one part of that, they can take it further.
And if people want to find more on your work, it's at ray.tomes.biz, which we've mentioned in the chat. Have you written books?
No, I've had about 6 goes, and I've discovered I'm much better at raving in person than I am at writing. But I'm gradually gathering it together. And after I've done these talks with the Cycles Foundation, I've decided that before the end of next year, I've got to put out a book. And my plan is it will be very cheap. We'll offer it through other people like yourselves who can get it even cheaper, can have a discount. And I just want to get lots of them out there. So it'll be electronic form only. I read about a woman who wrote novels, and she went along to probably Amazon, I don't know. Is that where people put their electronic books on Amazon?
Yeah.
And everything else.
I think so. So they told her you should charge $20. She says, no, I don't want to charge $20. I can't remember what she charged. It might have been $2 or $3 or $5 at the most. It was around that range. And they said, you won't make any money like that. She said, I don't care. And she did. She sold 10 times as many copies as any book had previously by charging a tenth as much. So she got the same amount of money, but she got a lot more people reading it. And then more and more came back for her next one. So she kept doing it that way. And I decided that's the way to go. I'm not planning to write more. One book would be my limit. Yeah.
Well, let's plan to talk again when you're writing the book or when you've written the book, because I think it'll be good to, after you've had a chance to get all those ideas aligned on paper. It'll be really fantastic to talk to you again. Yeah.
Okay. Thanks very much for having me. I've really enjoyed. I like you two people. You're lovely, and I like what you're doing. It's very great. Thanks.